In this video, we're going to talk about vectors. I want to do a review of vector notation. We're going to talk about what a vector is in terms of magnitude and direction. We're also going to look at vector operations, including addition, subtraction, and scalar multiplication, and talk about the geometric implications of those operations. So, to start with, for this book, there are many ways that you can represent vectors, but for this course, we're going to look at vectors as an ordered triple. So this is a vector because we see that our vector v has a little hat that indicates that it's a vector. You can also boldface the letter, and that's an indication that this is a vector. Another thing that you can see is that we offset the vector with these pointed brackets rather than curly brackets to indicate a point. So this vector, the first component is the x-coordinate, the second component is the y-coordinate, and the third component is the z-coordinate. So if we were to represent this vector in three-dimensional space, we would want to try to graph this on an x, y, z coordinate system, which is tricky, right? Because we only have 2 dimensions to work with when we're drawing on a flat piece of paper. And we're trying to represent something that's 3 dimensions using just a 2-dimensional space. The easiest way to do this is to set up a coordinate axis, and you can think of this x-axis as sort of projecting out towards you, like this is coming up out of the page at you. And so my x-coordinate is 3 units forward. My y-coordinate is 1 unit in the negative direction, so I'm going to travel -1 unit in the y direction. And then I'm going to travel vertically 2 units in the z direction. And that's something that's the hardest one, at least for me, to visualize. I'm going to think of making like a little box. This little box, this is the base of the box. I've traveled back 1 unit and forward 3 units. And now from this point, I'm going to travel up exactly 2 units in the z direction, right? Because this is sort of like the back corner of this box. And now that I've drawn this box, the vector in basic position starts at the origin and extends outward so that the tip of the vector is at the point 3, -1, 2. Whereas the vector itself could be anywhere in space, right? Usually when we represent vectors, we like to represent them in standard position, where the start of the vector is at 0, 0, 0, and the tip of the vector is at 3, -1, 2. But if I move this vector somewhere else in space, it would still be the same vector. It just has a different base point. Like, for example, this might be a vector that has the base point of 0, 4, 3. And meaning that it's 0 in the x direction, it's 4, 1, 2, 3, 4 in the y direction, and it's 1, 2, 3 in the z direction. This is the base point. We might want to find out, well, what does that mean in terms of where this tip point is going to be, assuming that our vector v still has the same components. The components 3, -1, 2. How can I visualize that? That means that I'm moving 3 in the x direction from this base point. I'm moving -1 in the y direction from this base point. And I'm moving 2 in the z direction from this base point, meaning that my tip up here is going to be equal to the point, maybe I'll call it P, is equal to the point 3, 3, 5, because it's given by the summation of each of these coordinates. And in this case, the summation is going to be, I'm going to call it a vector. Well, I guess it's a point in space. It's going to be 0 plus 3, 4 plus -1, and 3 plus 2. So that's a little bit about the geometry of these vectors. There's another type of notation that I want to mention, and that's the fact that we can also represent this in terms of standard basis vectors. So in 3-dimensional space, our standard basis is given by I, j, and k. Those are the initials that we use to represent the vector 1, 0, 0, which is just the unit vector pointed 1 unit in the x direction. This is my little vector I. The vector j, which is 1 unit in the y direction, and the vector k, which is 1 unit in the z direction. For example, our vector v here could be represented as 3 copies of the I vector because we're moving 3 units in the I direction. So you could write this as 3I plus -1 unit in the j direction, -1j, and then 2 units in the k direction. So this is an alternate way. If I didn't want to use this vector with these pointed brackets, I could also represent my vector v as 3I minus j plus 2k. So I haven't done anything to this vector. I'm just rewriting it using the standard basis vectors. Let's talk about vector addition and subtraction. Suppose I have 2 vectors. I'm just representing these vectors in 2 space because it's easier to visualize what's going on. Although you could, all of the properties hold in 3 space as well. It's just harder to draw. So let's say that we have a vector v and we want to add to it our vector w. Maybe I'll do an xy plane. So here's x, here's y. First, let's represent our vector v. It's 1 in the x direction and 2 in the y direction. My vector v. And my vector w is 3 in the x direction, 1, 2, 3, and -1 in the y direction. Now suppose I wanted to represent the vector v plus w. How would I do that algebraically? Really, it's just the summation of each of these coordinates. So in this case, it's going to be 1 plus 3, which is 4, and 2 plus -1, which is equal to 1. So I get the vector 4, 1. And I can draw that by going over 4 in the x direction and up 1 in the y direction. So that's my algebraic way to be able to write v plus w. Maybe you can't tell the difference in color. That's okay, though. How can I geometrically describe what happened with this vector addition? The easiest way to think about it is to think about starting with, well, I guess addition is commutative, so it doesn't matter which vector I start with, but I'm going to start with my vector v, and then I'm going to add onto it the vector w. Another way to represent that is to think about putting these vectors tip to tail, meaning I go the distance and direction of v, and then on top of that I'm going to add on my vector w, which in this case is going over 3 more in the y direction and down 1, and that gives us the summation v plus w. You could also think of it as w plus the vector v, which would mean that I would move in the direction of w and then add on to the tip of this vector my vector v. Because recall, a vector is a vector no matter where the base point is. I'm just choosing to visualize the base point of my vector v at the tip of w instead of at the origin. Similarly, we can think about vector subtraction, v minus w. Component-wise, it's going to be the components of v minus the components of w. So this is going to be 1 minus 3, 2 minus -1, which is equal to -2, 3. And I can also draw this -2, 3 is this vector right here. This is my vector v minus w. And how can I visualize this? Well, there are a number of ways to think about it, but one way to think about it is to add the negative of w. That's the way that I like to think about it. So I travel in the v direction, and then instead of adding on w, I'm going to add on the negative of w, which is w just flipped in the opposite direction. So negative w in this case, instead of being 3, 1, negative w is going to be the vector -3. Oh, sorry. Instead of 3, -1, it's going to be -3, +1. So I'm just adding the negative. So I travel in the direction of v, and then I travel in the direction of negative w, which is moving backwards 3 and moving upwards 1. So maybe this is my v and then negative w. So that's vector addition and subtraction. All of this holds in 3 space as well. It's just much harder to draw. Finally, I want to talk about scalar multiplication. So let's go back maybe I should cover this for confusion's sake. Let's go back to the original vector that we started with. Our vector v from the first example is this three-dimensional vector, and I've drawn a picture of it here. So this is moving 3 in the x direction, -1 in the y direction, and up 2 in the z direction, gives us this vector. What would it look like if we multiply this vector by 2? Scalar multiplication means I'm multiplying by just a scalar. What is a scalar? It's a real number, like the number 2. And when I multiply by 2, algebraically, I'm going to think of this, actually, you can think of this in terms of the distributive property, that I'm going to elongate each one of my coordinates by 2 units, by a multiple of 2, giving me 2 times 3, which is 6, 2 times -1, which is -2, and 2 times 2, which is 4. So that will give us a new vector that's 6 in the x direction, that's -2 in the y direction, and then +4 in the z direction. And so this vector is going to grow. It's still in the same direction. It's just going to be twice as long because I multiplied it by 2. Why is this interesting? Maybe I want to point out, what do I mean by twice as long? Let's talk about the magnitude of a vector. The magnitude of the vector is the same thing as the length of the vector. And how do we compute the length of a vector? The magnitude of our vector v, this is our original vector before we multiplied it by 2, is going to be the distance from this point, the origin, to the tip of the vector, which is at the point 3, -1, 2. So if I want to find the distance between these 2 points, I'm going to have to use a Pythagorean theorem that works in 3 dimensions. It's going to be sort of, if you think of it just as a triangle, it would be this base squared plus this length squared, square rooted, would give us the length along the bottom. And then we're going to have to do the same thing for this other right triangle, which is this length squared plus this length squared, also square rooted. Or we can do both those steps in one step and compress our Pythagorean theorem into the x coordinate squared, which is 3 squared, plus the y coordinate squared, plus the z coordinate squared, all square rooted. This is just Pythagorean theorem. Because these are all just right triangles. And when I do this, let's see, I get 9 plus 1 plus 4, it's going to be the square root of 14. And let's check that when I take the magnitude of twice of this vector, so I'm taking this vector and multiplying it by 2, that's what this scalar multiplication did. Let's see if we actually get twice the square root of 14. I'm going to look at, maybe down here, what is the magnitude of our new vector w? It's going to be the square root of 6 squared plus -2 squared plus 4 squared, which is 36 plus 4 plus 16, which is 50, let's see, 36 plus 4 is 40, plus 16 is 56. And notice that 56 is indeed, 56 is exactly equal to the square root of 4 times 14, right? Because 56 is just 4 times 14. And that means that I can take out this square root of 4 and I get 2 times the square root of 14, which is exactly what we wanted, that our original vector had a length of 14 and our new vector had a length of 2 times that 14. There's one final thing that I want to mention that's important in terms of scalar multiplication, and that's the idea of unit vectors. So unit vectors have length 1, and we can take any vector and sort of shrink it down. Let's go back to our picture. Let's say that we have our original vector v, and I want to shrink it down to just have a length of 1 unit. We'll see that having vectors of 1 unit are nice for making computations. So let's start with our vector v and shrink it down to be a length of 1 unit. How are we going to do that? We want it to have the same direction, and geometrically you can sort of visualize, well, staying along this path of this one line, I want to sort of shrink it down until I get exactly to a place that's 1 unit long. There are a number of different ways that you can approach this, but the easiest way, here we saw that if we multiplied the vector by 2, it would get twice as long. We don't want it to be twice as long. Right now it's square root 14 long. We want it to be 1 square root 14th of its length. Because right now it's at square root 14. If we take it to be 1 square root 14th of its length, that will be exactly 1 in length. Or in other words, we'll say that a vector w, maybe I'll say, is the original vector. And a new vector u is the unit vector for w. Or for v. If we have that u is exactly equal to 1 divided the magnitude of v times our original vector v. I shouldn't use this. Times our original vector v, which was v1, v2, v3. Or we can write it as our original vector v divided by the length of v. Because if I have something that's 10 units long and I divide it by 10, then it's only going to be 1 unit long. Or if I have something that's square root 14 units long and I divide it by square root 14, then it's going to be just 1 unit long.